ANTS, the Autonomous Nanotechnology Swarm, is a breakthrough in mission architecture for multi-platform missions to multifaceted targets such as asteroids. We will illustrate this architecture with the Prospecting Asteroid Mission, or PAM, concept. The breakthrough in mission architecture begins with the very first step, the process of producing components for an ANTS mission. The spacecraft systems are manufactured at an autonomous facility in space designed using the ANTS architecture. All components are constructed from carbon nanotubes reversibly spooled at NEMS multinodes, interconnected to produce a three-dimensional mesh acting as a platform. Specially designed nodes produce the carbon nanotube-based sail layer, which is attached to the sail platform to make the solar sail for a single spacecraft. Another platform, acting as the instrument and subsystem platform, is tethered to the sail of that spacecraft. All subsystems, including power and communication, are attached to the instrument platform as specialized nodes. Once the pieces are connected, they are stowed and the carbon nanotubes are reversibly spooled into the NEMS nodes for a small package volume, a 10 centimeter sided cube for a single spacecraft. A 1 meter cubic package, manufactured using super miniaturized autonomous reconfigurable technology, or SMART, will contain all 1,000 1 kilogram spacecraft. This SMART cube will be delivered to the Earth-Moon L1 Lagrange point for deployment. Each spacecraft will be released in sequence from the SMART cube. The self-deployment of each spacecraft from its SMART shell will be the reverse of the manufacturing scenario. After deployment, the recyclable SMART shell will reconfigure into a stackable and reusable rectangle for return. Carbon nanotubule tethers will be deployed from multifaceted NEMS nodes to form the frame for the sail. The lengthening-shortening process is completely reversible, and the nodes are flexible. Thus, the frame is extensively shapeable. A SMART instrument and subsystem holding platform, similar in design to the space frame, will be reconfigurably tethered to the frame. The sails will reversibly deploy over the frame from specially designed MEMS nodes. Sail and frame are changeable in shape and extent and are capable of forming tip vanes, making holes, and stowing sails as needed to assist in navigation and data collection. There are 10 classes of spacecraft specialists, identical except for their specialties, including 8 instrument classes or workers, plus communication specialists called messengers, and processing specialists called leaders. Subswarms will form and depart as groups of 100 spacecraft become available, with 10 from each specialist class. Over a period of 2.5 years, the swarm will travel on a solar sailing trajectory toward the asteroid belt. In each subswarm, imagers will perform remote detection of asteroids. Based on imager input and mission goals, leaders will select optimal targets. Each subswarm then navigates to its assigned target. Imagers collect data for a 3D model from stereo imaging, with possible inputs from other worker classes for further details near the target. Once the 3D model is adequate, clusters of workers of the same class move to optimal configurations for their data gathering operations. When leaders determine that the target has been adequately surveyed, data-taking operations cease, survey knowledge is shared, and a messenger is selected to return the data to Earth. Meanwhile, the subswarm moves on, the imagers initiating the search for new targets. All subswarms are simultaneously detecting, selecting, surveying, and searching for new targets. As a result, over the course of the mission, hundreds of asteroids will be studied.